Well, hi, grade nines. It's a beautiful day. Yeah, someone in the class asked me a question, and I thought maybe more of you might ask me this question. So anyway, like usual, I'm going to post this video with the explanation on OneNote, and it's already posted there. Now, before I go ahead and look at this question, which is page 243, number 4, I just want to point something out to you. Okay. If you remember when we were doing the sound unit before, in OneNote, there's a page that has all the formula on it. We used it for our last test. Okay, so I just want to show you where it is. You can see it here, sound formula. And if you look at this, there are a couple of things that I circled from before, but I'll just erase that. Okay, all the formula are here. Like here's the Doppler equations and stuff like that. But here there's speed equals distance over time. There's velocity equals frequency times wavelength, and so on. There's the relationship between frequency, cycles, and time, and so on. Speed of sound in various materials. And this has to do with the decibel scale here. This one here is this weird little graph is the decibel scale. Now we did do that before the break, but it wasn't on your test. We did that little hearing test, if you remember. But anyway, so it's there. So please use it. Okay, and of course, if we ever get around to figuring out how to do a test in the rest of this, and I think we will, okay, you can use this formula sheet. That's definitely allowed, okay? So anyway, now let's get back to this question. All right, so with that in mind, page 243, okay, it says here 200-meter dash along a straight track was timed at 21.1 seconds. That's an excellent time, okay? It's like getting to Olympic level there. By a timer located at the finish line who used the flash from the starter's pistol. Now they used to use, like they'd fire a gun, okay? And basically there'd be a flash of light. And then he started the stopwatch. The air temperature is 30 degrees. And it says, what would the time have been had the timer started the watch upon hearing the sound of the gun? So, see, a flash is light. Light travels faster than sound. In fact, light travels at 300 million meters per second. And so if you're just 200 meters away, that light is going to appear instantaneously. Like it'll take just like under a millionth of a second to reach you. So from your point of view, that flash of light is instant. There's no delay in the time. But the sound, on the other hand, travels a lot slower. Okay. So to do a question like this, okay, it says, what would the time have been if we use the sound of the gun instead of the flash of light, okay? So look, what you do is you go like this. First, we need the speed of sound. Whoops, that's a terrible looking. Okay, there you go, speed of sound in air. And there's a formula on the formula sheet, 332 plus 0.59 times the temperature. So you just go ahead and use that. The temperature is 30 degrees Celsius. So at 30 degrees Celsius, the speed of sound, I'll need my calculator, just give me a second. Okay, so 332 plus 0.59 times 30 equals 349.7. So this is 349.7 meters per second. Okay, so now you start your stopwatch, and that's what you get. Now, here's the thing, how much time, if it's a 200-meter straight track, okay, how much time would it take for the sound to reach you from the starter's pistol? Now the starter's pistol is located right next to the runners when they start. Okay, so that sound has to travel a distance of 200 meters to reach you. Okay, we're wondering how much time it takes, and we know the speed of sound is, I'll use the rainbow, is this number here. All right, so there's another formula on the formula sheet where time equals distance over speed. So 200 divided by 349.7, okay, that's equal to time, okay, that's equal to 0.572 seconds. So this would equal 0.572 seconds. All right, so here's the deal. Like if you've ever run in a race before or seen a race like this, they would normally say on your mark, set, and then you would hear bang, okay? Now that's if you're the runner and you start running. But this person is timing from the finish line and they don't hear the bang right away. See, if you're standing right next to the gun where the runners are, you're gonna hear that bang right away. But this is how much time it takes, that point size 572, that's how much time it takes for it to reach the person with the stopwatch, okay? And so what's gonna happen is, they've already started running, okay? So like the person will start their stopwatch, then the runners will start running. But this person has delayed starting their stopwatch by this amount because they waited for the sound to reach their ear. They didn't use the flash of light, which would arrive instantly. So this is a delay in the starting of the stopwatch. So therefore, the time for the race will be shorter. It'll equal the time that they actually did, which is 21.1 seconds. But then you're going to have to subtract 0.572 seconds delay of starting the watch. It's almost as if you started your watch late, so then the guy runs the race, and then by the time you stop the watch, because you delayed, he had already started running, it's going to seem like he ran it in less time. And this is the delay, right? We have to subtract that delay. So 21.1 minus 0.572 is 20.528. So I'm going to round that to 20.5. So it'll appear, that's rounded off, but anyway, it will appear as though the runner ran the race in just 20.5 seconds. In other words, that he was a little bit faster by not an insignificant amount, like over half a second. And if you're an Olympic runner, it's a big difference. So anyway, that's how you do question 4 on page 243. All right, guys, I hope you, if you have any other questions, just let me know, and I hope you're having a good day.